Hello and welcome to lecture 16 of Data 102. We are going to make a slight change to our plan from the start of the semester, in that today's lecture is going to be a fourth lecture on the topic of causal inference. All right, so the rest of the schedule is going to have to be adjusted slightly and pushed back a little bit. Okay, so and there are a few reasons why we're doing this. Okay, so the first reason is because the lab that you're going to get for this week is on the topic of instrumental variables. And it's only appropriate that we spend some time introducing what these are to give you some context. And the next reason is that instrumental variables is actually a really nice way to end the unit on causal inference, and it ties up all of the concepts that you have learned so far together in one setting. Okay, and really what this topic is about is trying to find a middle path between doing a randomized experiment, which is not always feasible, and doing observational studies where we need to rely on this unconfoundedness assumption, which is not always so reasonable. So let's start with a recap of what we know about observational studies. Okay, so first we defined this non-parametric superpopulation model, meaning that we now have a distribution for our covariates X, our treatment Z, and the two potential outcomes. Okay, so here we don't assume any relationship between Y, Z, and X. We just, we just have this model. Okay, and the notion of a cause effect is encoded into having these two potential outcomes. Our estimate of interest is the average treatment effect, denoted ATE, and this is going to be the unconditional expectation between the two potential outcomes. Okay, but what's the problem? The problem is that we don't actually see both outcomes from one person. And furthermore, these outcomes are not independent of the treatments. Okay, and so without making further assumptions, we can't really do much. And instead, we have to rely on this unconfoundedness assumption, which is that after we condition on X, then the potential outcomes are independent of the treatments. Okay, and as we said in discussion, one way to think about this is that within each level of X, okay, meaning that if you consider all of the units or all the people who have some value of X, say X is equal to A, then within that strata, we are essentially running a randomized experiment. Okay, so treatment is going to be essentially random there. Okay. And so if we have this assumption, then we can do something. Okay, and we discussed two different methods. The first method was so-called outcome regression, where we try to fit a model for the outcomes for the conditional expectation of the outcomes, y1 and y0 given x. And then the second method was inverse propensity score weighting, where we had to estimate the propensity score, which is the probability of being treated given your covariate X being equal to some value. All right, and so the big question that arises from this discussion is, can we find a way around this unconfoundedness assumption, which sometimes is just not so reasonable? All right, and we're going to have a partial answer, which is this idea of instrumental variables. Okay, and so here's the overview for the rest of this lecture. So to start, we're going to define a class of causal models called linear structural models. And here, we're going to move away from this non-parametric framework that we had in the previous lecture and assert some linear structure between X, Y, and Z. Okay, and this is going to allow us to simplify and come up with some estimators that make use of this linear structure. Okay, and now in the context of these linear structure models, which I should say are very common in social sciences, especially economics, so we're going to talk about problem of confounding in these models, and this is also known by the name of omitted variable bias. Okay, so what happens when you omit a variable from a linear regression? All right, and so this is so this is going back to So what can go wrong whenever there's unmeasured some x that you don't measure, and so you can adjust for it. And then we're going to introduce this idea of instrumented variables, which allows us to overcome this problem of unmeasured confounding. Okay, and then there's a very mathematical definition of what instrumented variables are. We're going to try to make this concrete using some examples. Okay, and finally, we're going to talk about some extensions of instrumented variables, at least the basic setting, to some slightly more advanced settings. Okay, so hope you enjoy the rest of this lecture. In fields like economics, it is typical to depart from the non-parametric setting that we have been considering so far, and instead work with some structural models. So what are structural models? So these are usually parametric models that place some restrictions on the joint distribution and causal relationships of all the variables. Okay, so this places some restrictions, but it also makes it easier to estimate the parameters of the model. All right, so the class of such structural models that are the most popular and also perhaps the easiest to work with are the so-called linear structural models. And so in the first part of today's lecture, we're going to introduce what these are. Okay, so here's the definition. Okay, so we will work with the linear structural model defined by y is equal to alpha plus tau times z plus beta transpose w, beta transpose x plus epsilon. Okay, so y is the outcome variable, z is supposed to be the treatment variable, and x is some other confounder. All right, and epsilon is your noise, and we assume that epsilon is so-called exogenous. Okay, so this is a common term in economics, and what it means, at least in our case, is that it has mean equal to 0 and is independent of x and z. Okay, and sometimes we further assume that epsilon is a normal random variable, but this is not strictly necessary. Okay, so as I said before, so y is still the outcome as the outcome variable. Z is a treatment variable. And x is a confounder. Okay, and here's a subtle remark. Okay, so we usually add the additional equation that the treatment z is also affected by the confounder x. Okay, so you can write it as a function of x and delta, where delta is again an exogenous noise variable. Okay, so mean 0 and independent of x. Okay, and f is a function that encodes the structural relationship between x and z. Okay, but okay, so we're going to leave this implicit. Okay, so you don't really have to worry about this. Okay, so instead, all you need to know is that we allow for X and Z to be correlated. Okay, so the covariance between them could possibly be non-zero. All right, so this is a linear structural model. And I'm just going to mention that this is not the same as the linear model that we've learned in the section on GLMs and also in previous classes. Okay, so this is not the same as the linear model you've seen previously. Why? Because last time when we talked about linear models, that was about the joint distribution of the variables. Okay, so previously, okay, so that was about the joint distribution of y, x, epsilon, etc. And this means that it was only about associations. Okay. So it tells you nothing about the causal relationships or what happens when you intervene and change one of the variables. Okay. On the other hand, that is exactly what a linear structure model is asserting. Okay. Okay. So on the other hand, a linear structure model, which I'm going to denote by SM, okay, encodes assumptions about intervention. And so what this means is that if we okay, so we have some unit I, so like some person. So if we could set Ci to be equal to 1, so we set the treatment indicator to be 1 for unit I, then we will observe the outcome under treatment. So this is going to be the potential outcome yi of 1, right? And this will be given by the formula tau times z, but z is equal to 1. So this is just tau plus beta transpose x, xi plus epsilon I. Okay. And alternatively, if we could set Ci to be equal to 0, then we will observe the other potential outcome, yi of 0, which is given by, okay, so no more tau now, because tau times z is equal to 0. Instead, we simply have beta transpose xi plus epsilon I. Okay, and note that it's the same epsilon I for unit I. Okay, and so if you have a linear model, there is no such assumption. It just tells you about the associations that you see in the data. Okay, so this is different. And here we're talking about Z binary. And of course, in the linear model, Z need not be binary. And in that case, we're gonna have one potential outcome for every single possible value of Z. Okay, so it's possible to think about potential outcomes in that way, but for this lecture, and in fact, in a lot of papers, we usually just stick with a binary treatment because it is just sufficient for the topics that we want to think about. Okay, so this shows that the linear structural model is actually a special case of the potential outcomes framework. Okay, and more than that, okay, so we also see that the ATE, okay, so we see that the ATE for the linear structural model is equal to tau, right? And in fact, we see that not only is the ATE equal to tau, the individual treatment effect that we never get to observe in practice okay, for every unit is actually the same. Okay, and just to write down the definition, okay, so it's yi1 yi1 minus yi0, and this is going to be equal to tau. Okay, if you just compare these two formulas, the difference is tau. Okay, and so you can see that this is another, this is sort of built into the model. And this constant treatment effect is not something that is assumed in the general setting that we talked about in the previous lectures. Okay, so this assumption might be reasonable or it might not be. Okay, so now we can see that given the model, we have unconfoundedness. Okay, so to recap what this means that the potential outcomes are independent of the treatment given X. Okay, so you can check that this holds. And so any of the methods that we talked about previously, IPW or outcome regression, can be used to estimate tau. Okay, but even better, we know that the structural model is linear, so we might as well run a linear regression. Okay, so we can use the previous methods, or we can also estimate tau by running a regression y on x and z jointly. Okay, and this is what people do often in the social sciences. We assume a linear structural model, we run a regression, and we say that based on our assumptions, we know what the treatment effect of some covariates. Okay, and now let's talk about the way in which we can represent this model that we've talked about so far. Okay, so this is the so this is going to be the notion of causal graphs. Okay. Okay, so causal graphs can be used to represent the model as follows. Okay, so we have our treatment, and it's going to have a causal relationship on y. And then we have our confounder that has a causal relationship on both z and y. Okay, and so how to interpret this? Okay, so first, arrow from x to, arrow from z to y implies that z causes y, right? And this is just the fact that z is inside this the structural equation. Okay, so z is here. And so the arrows, similarly, the arrows from x into z and y means that x causes both z and y, as we saw in the structural model. Okay, so this is something actually new from what we said in the previous lecture. Okay, so as opposed to the potential outcomes framework, here in the structure model, we can talk about the causal relationships between the other variables. So not simply the treatment and the outcome, but also between the confounder X, the treatment Z, and also the confounder and the outcome. Okay, so this is something that's new. Okay, so we have introduced linear structural models, and we saw that if we observe all the variables, we can perform regression and estimate the ATE and everything else we want. Now, let's suppose that we do not get to observe X, and so we have what is called confounding. Okay, so in this linear structural model setting, confounding is going to happen via the so-called omitted variable bias, which I'm going to define for you shortly. Okay, so here, to repeat, we do not observe X because maybe we just don't have data on X, or maybe we are just not even aware about X. Okay, so there might be some hidden confounder that we just don't know about because we just don't have enough information about this field of knowledge. Okay, so let's try to, so we don't have X, so all we can do is to regress Y on the treatment. And let's see what happens. Okay, so let's define tau or S to be solution to the least squares equation where we minimize alpha and tau. Okay, so this tau is not a variable, it's not the treatment effect of this least squares equation, alpha plus tau Z minus Y. Okay, and so this is like a population least squares. Okay, so a finite sample will really be the sum over all the samples, but now let's assume that we have infinitely many samples. Okay, so with this definition, okay, so we know, okay, so in finite samples, we know that the formula for this is Z transpose Z inverse times Z transpose Y. And in infinite samples, this is going to be the covariance between Y and Z divided by the variance of Z. Okay, so this is by definition, but now we can write out what this is. Okay, so let's expand Y in terms of its definition. So this is going to be alpha plus tau Z plus beta transpose X plus epsilon. And we take the covariance of this with Z. Okay, so now what happens? Okay, so alpha is constant, so we can cancel it. Epsilon is independent of everything else. We can cancel it. And so we're left with the two terms remaining. And so let's try to separate them. Okay, so Z yeah, so let's try to separate them, and covariance is linear in each of the inputs. So this becomes tau Z, covariance of tau Z with Z divided by the variance plus covariance of beta transpose X with Z divided by variance of Z. And now the first term is just going to be tau. And the second term, okay, we can take the beta transpose out. It becomes beta transpose times covariance X with Z divided by variance of Z. Okay, so we see that if what we want to do is estimate the treatment effect, which is tau, then we're left with this bias here. This term over here, oops, this term here, and this term is called the omitted variable bias. Okay, and that's bad because it means that if we don't actually observe Z, observe X, then perhaps there's no hope to try to estimate the true treatment effect of Z on Y. Okay. So now to make things more concrete, let me just give you a few examples of confounding. Okay, so we already seen some in the first lecture on causal inference. I'm going to give you a few more here. Okay, so maybe the treatment is health insurance. So whether or not some person has health insurance. And then Y is health outcomes. Like you can think about this in terms of like life expectancy or risk of getting cancer or other illnesses. And then what's a confounder? Okay. So confounder X can be socioeconomic background. And usually, okay, you see that socioeconomic background is a standard confounder, but it refers to many things like including their lifestyle and also the strength of their social ties. Okay, so we see that so it's natural to see that socioeconomic background is going to both influence your health outcomes and also whether or not you are going to have health insurance. Okay, so here's a second example. So Z is military service. Okay, so whether or not you served in the military at some point. And then Y could be your lifetime earnings. Okay, so maybe you'd be interested in the effect of serving in the military on your lifetime earnings. But again, this is going to be confounded by socioeconomic background. Okay, so people from less privileged backgrounds are more likely to serve in the military. And so these people are likely to have less lifetime earnings simply because of lack of other opportunities. Okay, so definitely X is going to be a confounder. So third example. Now the treatment of interest is family size. Y is whether the mother in the family is employed. Okay, so we want to investigate the effect of family size on whether the mom is employed. And again, X can be socioeconomic background. Okay, so everything, socioeconomic background is such a broad term that it really is a confounder or a possible confounder for everything. Okay, and maybe, yeah, so I have more examples in the notes. So maybe I'm just going to stop here. Okay, so the big question here is why can't we just not adjust for confounding? And I kind of said this earlier already. Okay, so the reason is because sometimes it's just not possible to collect the data on the confounders, right? So it's expensive to collect data, and sometimes it's somehow it's just not recorded, and yeah, so you have just no access to for instance, all the socioeconomic data about people who you want to study. Okay, and then another reason is because there could be possible confounders X that we are just not aware about. So for instance, socioeconomic background is a broad term. Okay, you can think of this in terms of your parents' income or that you can sort of measure through tax returns. But then you also might include many other factors like how strong are your social is your social ties, you know, other family background reasons, maybe personality traits. So I'm not quite sure if that comes in social economic background, but these are all things that are going to be extremely hard to measure, and you just don't know. Okay, so there could be many, many other things that could be confounding the relationship between Z and Y, and maybe it might even be hard to put them all into words. Okay, so in that case, whenever you say that, okay, I measured some X, I adjusted for it, somebody else who does not like their conclusion can come back and say, okay, what about these other confounders? Okay, so they can just keep doing this. And in fact, this is what happened with smoking. Okay, so there's always going to be a constant cloud of doubt over any causal conclusions that you try to make. Okay, so that is simply what happens when you try to work with observational data. Okay, so the big question is this. Is there a middle way between randomized experiments that we know are good and that we like, but are also sometimes not so feasible, and using the unconfoundedness assumption that you just seen is sometimes not so reasonable. Okay, and the answer turns out to be yes. Okay, so there actually is something that's in between, and this is the idea of instrumental variables. Okay, and what's the idea? The idea, okay, so the big idea is that nature sometimes is good to us, and it provides us with a partial randomized experiments. So not necessarily a full randomized experiment, but something that's partial. And what I mean by this is that we have a variable called the instrument that is truly randomized. And this instrument is going to be used to inject an element of partial randomization into the treatment of interest. All right, which we saw in the previous section could be serving in the military, could be health insurance, or something else. Okay, so this is the idea of instrumental variables at a very high level. And so what we're going to do right now is to first define what it means mathematically, and then I'm going to return to the examples that we had earlier and try to illustrate what it means for those examples. All right, so here's the mathematical definition. Okay, so let's assume the linear structure model defined above. And now let's further assume a variable w such that we can write the treatment z as a linear function, okay, alpha prime, not the same as alpha before, so some other number, plus gamma times W plus eta. And we need some assumptions on these quantities. So gamma has to be non-zero. Okay, so this is the so-called relevance assumption. And then W has to be independent of the confounder X and also epsilon, the noise. And this is the assumption of exogeneity. Okay, and again, eta is also going to be an exogenous noise variable that is independent of everything else. Zero. Okay, and so under this model, such a W is called an instrumental variable. All right, and here you have the definition. Now, let's see how we can use the instrumental variable W to identify the ATE tau. And so it goes as follows. Let's first compute the covariance between Y and W. Writing this out, we have, okay, so let's expand this in Y as before. We get alpha plus tau Z plus beta transpose W. Keep speaking, beta transpose X plus epsilon, and then we take the covariance of this with W. And now let's see what happens to the terms. Okay, again, alpha constant disappears. W is independent of X and epsilon, so these two disappear as well. And so we just get the Z term remaining. Okay, so let's pull the tau outside. We get covariance of Z with W. And now we can further expand Z in terms of our structure equation. And this becomes alpha prime plus gamma W plus eta W. And again, you can cancel these two terms. And so we're left with tau times gamma times variance of W. Okay, so the emitted variable bias goes away, but we have this additional gamma factor. Okay, so how do we get gamma? Okay, so we can use a similar computation with Z and W. And this is going to give us gamma times the variance of W. And so we put everything together. Okay, so we have tau is equal to covariance of Y and W divided by the variance of W. And then, okay, so in the first equation here, we're going to shift gamma and variance W to the left-hand side. And so we're going to divide by gamma. But using the second equation here, we saw that gamma is going to be equal to covariance of Z and W divided by the variance of W. Okay, and so now we have an equation for the ATE tau. And in fact, right, so we can interpret this. So the numerator is just the regression coefficient of W on Y. Okay, so we regress Y on W. And the denominator is the regression coefficient of Z on W. All right. And so in finite samples, this tells us what we can do. Okay. And so changing this to a plug-in formula is going to give us the so-called instrumental variables or instrumental variable estimator, tau hat IV, and this is going to be W transpose W inverse W transpose Y divided by W transpose W inverse W transpose Z. Okay, so here let's assume that W has mean zero, or W is centered. Okay, so not able to do the centering. And here, just note that we are abusing notation here. So, okay, so here we are abusing notation slightly. And previously, we've used W, Y, and Z to denote the random variables. Here we're going to use them to denote the entire vector of observations, okay, from our samples of size M. Okay, so let me write this out. W, Z, Y denotes vectors of observations. Okay, and now here's another interpretation. Okay, so if we go back to the case when Z is binary, we can actually compute what the covariance terms are. And if you do that, okay, so this is going to be left as an exercise. We can show that the IV formula takes on a special form. It's going to be the difference between the potential outcome, or sorry, not the potential outcome, but it's going to be the difference between the conditional expectation of the outcome given W is equal to 1 minus conditional expectation when W is equal to 0. And then we're going to divide this by conditional expectation of the treatment Z when W is equal to 1 minus the conditional expectation of Z when W is equal to 0. All right. And so we can see that the treatment effect is really going to be a ratio, right? Because we know the way to interpret this is that the instrumental variable affects the outcome, but it only affects the outcome to Z, right? And you can think of the denominator as the proportion of, okay, if Z is also binary, okay, this is the proportion of individuals for whom Z flipped or Z switched. And then the numerator is going to be the observed change in Y, but because the treatment Z did not change for everyone, we have to divide the numerator by the proportion of people for whom the treatment actually changed because of the instrument. Okay, and we can see that the numerator and the denominator are both they're both some value of prima facie treatment effect. Okay, so recall that definition from the previous lecture. And in fact, it's sort of measuring the ratio of the prima facie treatment effect of W on Y and that of W on Z. Okay, so it also has that interpretation. And now let's go back to causal graphs. So let's see how we can represent instrumental variables in terms of causal graphs. So we had the diagram from before. And now I'm going to use circles to denote variables that we observe. And then I'm going to use a square to denote the variable that we do not get to observe. Okay, so we don't actually observe X. And then instruments is going to be denoted like this. Okay, it's a node W that points only into Z. Okay, and so why is that the case? That's because W is exogenous, and so it is independent of X. All right, so nothing actually causes X, W, and none of the other variables that we have here cause W. And then W is going to have some effect on Z. That's the relevance term assumption. And also baked into our equation is a further assumption that W only affects the outcome Y through its effect on Z. Okay? And so this causal graph gives a nice graphical representation of how or what the instrumental variable is about. Okay, and one final remark in this section. Okay, so it's important to bear in mind that we do not even have to be aware of X in order for instrumental variables to work. And so instrumental variables, if we have one, is going to get around that huge problem that we talked about earlier of having some potential confounding that we do not even know. And so this is going to help us make our arguments about causal relationships even more rigorous. Let us now revisit the examples that we talked about earlier in the lecture. And now we can see how one may use instrumental variables to get around the confounding involved. Okay, so the first one is about health insurance. And actually, this was the topic of one of the examples about experiments that we talked about 2 lectures back. Okay, so this was the 2008 expansion of Medicare in Oregon. And so people in 2013, okay, so Baker and all, use this 2008 expansion of Medicaid in Oregon. And remember that the way they did it was via lottery. Okay, so for those people who are applying for health insurance, they had a lottery and selected a random fraction of that population to be eligible to enroll in Medicaid. Okay, so W here is the lottery assignments. Okay, and recall in our discussion then that the lottery assignment was not the same as health insurance because only a fraction of the individuals who won the lottery ended up enrolling in Medicaid. And on the other hand, some people who lost the lottery did end up enrolling in Medicaid through some other means. Okay, and so we're not actually able to randomize health insurance, but we're able to randomize the lottery, which acted as an encouragement for people to take up health insurance. Okay, and in that sense, W, the lottery assignment, was an instrumental variable. Okay, so the second example was military service and lifetime earnings. Okay, so here, a paper by Angrist in 1990 used the Vietnam era draft lottery as the instrument W. Okay, so what happened was that there was the draft back during the Vietnam War, but not everyone was drafted. So instead, they look at all the birthdays, and then they sort of permuted they had like they randomized the priorities of all of the birthdays. And so, for instance, if you're born on like April 3rd, for instance, they might randomize you to have the highest priority. And then another date, like September 5th, for instance, would be the second priority, and then so on and so forth. So all of this was randomized. And so if your birthday was higher up on this draft lottery, then you're more likely to be drafted. And likewise, if your birthday was low on this, had like a lower rank, then you were less likely to be drafted. Okay, but then again, this is not a sure thing, because sometimes people could be exempted from the draft because of education or medical issues, etc. Okay, so again, here the lottery for the draft was not the same as actually undergoing military service, but you can think of it as leading to and causing an increase in the probability of serving in the military. Okay, and here you see that in the previous example, the randomization came from an explicit desire to do an experiment. And in the second example, this was something that's post hoc. Okay, so the randomness here was not intended for an experiment at all, but it turns out that many years later, people figured out how to make use of it in order to reason about this issue in econometrics. Okay, so the third example is even more funny. Okay, so here the intended treatment is family size, and Y is going to be an indicator of whether the mother in the family is employed. Okay, so here, Angrist, same Angrist as before, and Evans, and 98 used sibling sex decomposition as the instrumental variable. Okay, so why is this the case? Okay, so this is because first, this is random. Okay, so it's random. So here is really an indicator whether or not the children, whether the first two children born to the family were of the same gender or whether they were of different genders. Okay, so we're making use of the fact that sex of a baby is essentially random in some sense. And then at the same time, it also has this, it definitely has some relevance in the sense that it's known that families who have children of the same gender are more likely to have another child. Okay, so it's definitely going to have some amount of causal relationship on family size. And at the same time, it is random and so exogenous and does not depend on their socioeconomic backgrounds. Okay, so let me give a few more examples here. So example 4. Okay, so Z is going to be years of schooling. Y is salary. Okay, so yet another very natural question. We want to know whether if I go to school for a few more years, is it going to increase my salary? And so the confoundant here, again, is socio-economic background. Okay, so people from more privileged backgrounds are likely to go to school for longer. And so here, what some researchers did, okay, so this was a study by Chart from 93. And what he did was to use the geographical variation in college proximity as the IVW. And what I mean by this is that, okay, so here W is going to be an indicator in some sense of whether the person lived in close proximity to a four-year college. Okay, and here, to check the IV assumptions again, okay, so first, living closer to a college is going to increase your probability of going to that college because it's just more convenient for you. Okay, so it has relevance. But at the same time, we can think of this variation as being completely unrelated to the socioeconomic backgrounds. Okay, so here maybe the assumption is a little bit more tenuous, but it's one that you can argue for, and that's probably what happened in this paper. Okay, so 4 examples of instrumented variables. And so let me now mention a few remarks. Okay, so it's not a given that in any situation you can come up with an instrumented variable. It requires some degree of ingenuity. Okay, and you can see that some of these are pretty funny. Okay, so like the sibling set decomposition. Okay, you have to be pretty smart to think about this. And so this guy, Joshua Angrist, whose name appears on, I guess, 2 of the examples here. So he is one of the key figures in the development of instrumented variables, and he's a master at doing just this, of coming up with very ingenious instrumented variables. Okay, so Joshua Angrist is he's an economist at MIT. Okay, so if you think this is very interesting, you can look up more of his work. And then, of course, it's not a given that you can find an instrumented variable. So there are many cases of hypothesis that we want to test that we just cannot really come up with an instrumented variable. Here, one of this is just smoking and lung cancer. Okay, so it's hard to really come up with a good instrumented variable for that situation. Okay, so now, in the last part of this lecture, we're going to talk about some extensions of the instrumented variable framework. Okay, so the first extension is to the setting of multiple treatments or instruments. And what I mean by this is the case when Z, the treatment, is not necessarily just a scalar, it can be a vector. So maybe you're interested in the joint treatment effects of maybe years of schooling and also something else. I don't know, job training, for instance, on your salary. Okay, so this would mean that you're going to have 2 variables, an indicator for or variable for years of schooling and another indicator for whether or not you underwent job training. And sometimes instruments may also be vectors. Okay, so you might have more than just one instrument. And in that case, the IV estimator that was just going to be a ratio is not really going to make sense. Okay, so we're going to have to reformulate IV in a slightly different way. Okay, and this is going to be the method known as 2-stage least squares. Okay, so this is the method that you'll be using in the lab. And I'm just going to mention it here. Okay, so one thing to note is that it's going to be exactly the same as the IV estimator for scalar treatment and scalar instrumented variable. Okay, so how does this work? So first, let's define Z tilde to be the conditional expectation of the treatment Z on the potential outcome, on the instrumented variable W. Okay, and so now let's observe that because of the linear structure equation relating Z and W, Z is going to be simply equal to gamma times W. Z tilde is going to be that. Okay, so we call that Z is equal to alpha prime, plus alpha prime. Okay, so this is alpha prime plus gamma W plus beta. All right, and so now if we regress y on Z tilde, the regression coefficient that we get is, okay, by definition, it's going to be covariance of Z tilde with y divided by the variance of Z tilde. Okay, and now we can expand out y as before. Alpha plus tau Z plus beta transpose W, beta transpose X, as epsilon divided by the variance of Z tilde. Okay, and as before, we can do a bunch of cancellations. Okay, so first, okay, so Z tilde, okay, so we call that this is equal to gamma W, right? So we can cancel out alpha, epsilon, and also X. Okay, and so we're going to be left with the covariance of Z tilde with tau Z divided by variance of Z tilde. Okay, and we can take the tau out. Okay, so you have tau times this quantity. But then if you think about what Z tilde is, okay, so it's just a conditional expectation. So the covariance of Z with its conditional expectation is going to be the variance of the conditional expectation. Okay, and that's something that you can check. Okay, so more precisely, okay, so I can write this as covariance of Z tilde plus Z minus Z tilde. Okay, and you can check that this is going to be just the covariance of the first two terms. Okay, the last term is going to have no correlation with Z tilde. Okay, so this is just a property of the conditional expectation. Or you can substitute Z and Z tilde with their expansions in terms of W, and then you can also do the same thing. Okay, so the upshot is that this is just going to be equal to tau. And so we found another way to try to estimate tau. Okay, and so this is what happens in infinite number of samples. For finitely many samples, we can transform the argument above into an algorithm. Okay, and this is going to be called two-stage least squares, or 2SLS for short. Okay, and so let's write down the two steps. So step one, we regress treatment Z on W, the instrument, to get a Z tilde, which is defined to be W times gamma hat, where gamma hat is the regression coefficient. And so this is going to be WT, W inverse WT gamma. Sorry, WTZ. Okay, and also I just want to mention that here W is going to now include the constant coefficient. Okay, so that's why we don't have to worry about the constants anymore. Okay, so I mean, like, what I mean here is that alpha prime is going to go into W as well. step 2, we regress y on z tilde to get ahead two-stage least squares, okay, which is defined to be z tilde transpose z tilde inverse z tilde y. Okay, and that's the algorithm. And something that you can check is that whenever the treatment and the instrument are scalar, then this two-stage least squares estimator is exactly the same as the IV estimator. Okay, but the benefit is that now we can apply this to the case where Z and W are vectors. Okay, so that's one extension. And another extension is to turn this, to take this approach of instrumental variables and think about how it applies to the non-parametric setting. All right, so previously, instrumental variables, okay, so we define them in the context of linear structural models, and all the estimators and the theory that we have developed is all for that model of that structural model. Now the question is, if we drop that structural assumption, right, which sometimes you want to do because you don't want to make such a strong assumption, then can instrumental variables still make sense? And it turns out to be the case. Okay, so, and this is going to be the case for the binary treatment setting, or the binary instrument setting. Okay, so we call that, you can write, in this case, we can write tau as this difference in, sorry, this ratio in the prima facie treatment effects of the instrument W and Y, and then the instrument W on treatment Z. Okay, and so this actually has a meaning that holds in the non-parametric setting. So just potential outcomes and without the linear structural assumption. Okay, and all you need is a different assumption, okay? And a different assumption called monotonicity. Okay, but that is going to be an advanced topic. Okay, so in the notes, I'm going to link the paper for you that does this. Okay, but I'm just gonna stop here and say that, you know, it's nice to be aware of this, but again, this is out of the scope of this course.